Welcome to Project 3.4, Pin Change Interrupt. In this project, the goal of it is to increase the 7-segment display every time either the button on the left is pushed and changes states, or the rotary encoder is turned clockwise, which increases by 1, and counterclockwise, which decreases by 1. When the rotary encoder is pushed inwards, it resets it to 0. I'll demonstrate this later. On the right is a reset button that resets the entire code, and then, as I said, reset to 0. This project makes extensive use of interrupts. To do this, a few things have to be done. Firstly, the general interrupt mask register has to be set to allow interrupts in the port you want. This one here is for port B, and this one here is for port A. I start both. Port B functions as the interrupt for the button. When the button is pushed, it's triggered saying, hey, let's increase the number by 1. This one's a bit more complicated for A because that's where the encoder works. I'll get back to that in a second. Next, the general interrupt flag register. These appear when an interrupt has happened. However, it's a bit odd. They're only cleared when you set them to a 1. A weird little quirk that Atmel decided to throw in. These two essentially function the same, but for different ports. PC mask 1, or pin change mask register 1, it's a pretty long name, is for port B. I use port B pin 0, also known as PC int 8. Meanwhile, on port A, or pin change mask register 0, I use all of the interrupts from 0 to 2. These serve for the A, the B, and the encoder button, all coming from the rotary encoder. Now, because I've only started these as interrupts, these do not get used as interrupts, meaning they're free to do whatever they want without any interference on the interrupts themselves. That means I could use these as outputs, which I do, or these as outputs, which I don't do. Here's how the rotary encoder gray code works. Firstly, we have the detente positions. In the case for this encoder, it's 1, 1, and 0, 0. Next, we have the intermediate positions. These will appear when it's transitioning between the detente positions. In the case of this encoder, it's 1, 0, and 0, 1. So, how do we tell which direction it's going? Because if we look at the two detente positions, it goes 1, 1 to 0, 0 to 1, 1. Now, if we go backwards, it's 1, 1 to 0, 0. How do we tell the difference? Well, there's actually a fairly simple way to do this. So, we start at 1, 1. We move clockwise towards 0, this way. Now, it'll pass through with the intermediate being 1, 0. So, what happens if we XOR the intermediate and the final detente? Well, that's exactly what we have going right here. We XOR the intermediate and the detente, and we get 1, 0. Okay, what if we do it for a later position? For example, moving from 0, 0 to 1, 1 clockwise. Well, the intermediate is once again 0, 1, and then it's 1, 1. XOR them together, it's the same thing. That's because when you XOR an intermediate and the final detente, you'll always end up with a constant. This constant remains, well, constant, no matter in what section of the code is happening. It only matters the direction of which it's rotating. Now the same is true for counterclockwise. When we rotate counterclockwise, it goes from, say, 0, 0 to 1, 1. Okay? 1 0 XORed with 1 1, well, that's 1 0. And the same is true for here. And now we can see the pattern. With the counterclockwise having a constant and the clockwise having a constant, if we XOR the final detente and the intermediate together, we'll get one of the two, we reference it, and there we go. We have figured out which way the encoder is turning.